Ned, welcome to the podcast.
Thank you for having me.
Yeah, it's great to have you on. I'm really looking forward to talking about material and polymer selection. It's one of the things that is not talked enough about in MedTech for, modern catheters and delivery systems.
Yeah, come from polymer science PhD, so I spent way too much time worrying about all the physics, engineering, and chemistry that makes up the polymer world for sure.
Yeah, I think in polymer selection, I think a lot of people just use what they've used before or a predicate, and there's more to it. I'm from a real world perspective. I'm working on a project right now for a company I'm involved with called Anchor Balloon, and there's an extrusion on the distal end of the catheter. It's a distal end; it needs to be flexible, right? Um, it also, because there's an RX port coming in, it can't really have, it has to have minimal elongation. So these are trade-offs, right? Fighting against each other. It needs to bond to a balloon on the distal end, a nylon balloon, and a laser cut hypotube. Metal's plastic. So there's all kinds of variables. And you'd think finding a solution would be simple, but it's not. It's a challenge to get a material that has that strength, but flexibility, but no elongation. So sometimes you look at, well, what kind of additives can we put into it? Nanoclays, glass, or whatever. Is that a solution? So that real world experience really got me excited to kind of talk about this. And before we get into some of the items, what we're talking about here is this. Let me just share this. This polymer selection guide that you at Saint-Gobain developed, and it's very comprehensive. From test to chart, polymer selection for medical devices. And before we kind of get into some of the items within it, there's 13 kind of categories, and that's awesome and very comprehensive. We don't have time to go through them all, but good news is we'll make it a multi-part series, right? Maybe 2 or 3 different episodes to go through it. But let's kind of start with just kind of what's the problem with polymer selection and today, and tell us how this guide works as a selection guide.
Yeah, so I'd say the major point, even though every single graph here will have specific points, is that polymers are ranges of everything. There is they think of polymers as very long spaghetti chains. We are not perfect at making them equal length. They will be varied. They will have, some will be longer, some will be shorter. And because of this inherent dispersity, you will see definitely changes. Everything is kind of more of a gap or some type of curve within the polymer world. So you'll see data sheets that normally have one data point. And this is normally a specific history involving how quickly that was pulled, the processing conditions, and then you extrapolate. If you extrapolate that, and you expect it to work the exact same in a real world condition, that's where you potentially can run into problems. And then you combine that with, so from what I looked into from here, there's about 40 polymers, I'd say, that are like heavily utilized within the medical device world. That's a lot. And so people, you use what's worked before, and maybe you don't exactly understand why that worked before. And then if you start taking that into a slightly new environment, you might start running into issues that are more inherent to the material that may not immediately be exposed to themselves.
That's a good point about kind of taking a predicate and putting into it a different environment. And that can be taken in different ways, whether it's chemical, temperature, but also therapy, right? And I think when I came up with some of the topics to talk about out of the 13, in my mind, I'm thinking about more modern catheter systems for neurovascular, which need to be really super soft and flexible to navigate the tortuous intracranial vessels. Structural heart applications, usually have to have multi-durometer sections, stiff on the proximal, kind of very flexible on the distal, thin wall, delivering a large, TAVR device, and electrophysiology or PFA, where we're delivering energy. So we have to have materials that are tough and resilient for energy delivery. So let's go through some of these. In particular, I want to discuss 5 kind of categories here. Mm-hmm. And starting with kind of the focus on stiffness versus toughness and variable stiffness. And like I said, there's for these 3 high value, high growth markets that I'm thinking of: neurovascular, PFA, structural heart. This is real important. So talk about some of this particular item on the Polymer Selection guide: stiffness versus toughness.
Yeah. So I'd like to first throw a little bit of, I am not a catheter engineer. So everything I say, please take with a little bit of salt for sure. But I'd say from what makes catheters so intriguing from the material side is the fact that we ask always opposite things to work together. You need stiffness and toughness. These are normally, and we'll talk through, this is not the only time we're looking for 2 almost opposite like properties in the exact same device. So I think, so normally the way or shorthand you're going to use is you're going to be durometer. You're going to expect if the material is harder, it will, higher durometer will be a stiffer, lower durometer will be more flexible. What's more interesting, I would say, is the fact of, so you're normally looking for flexibility, and a big thing though is also like kink resistance. And so kink resistance for people, it's just when you're the buckling of the tube when you're bending it. But what's even more interesting is like, these are not, kink resistance is not exactly a material property. It's more of a geometric constraint. So you can see why when people are optimizing for kink resistance, you can get a lot more kind of bang for your buck by slightly adjusting maybe the wall thickness or the outside kind of the diameter of the tube, mm-hmm. versus making major efforts into the material. That's why you see a lot of really interesting laser etching, and all the beauty of physics can really get you a kink resistance, but the materials itself, you're going to see a less change within that system. But then an interesting kind of I'm going to drag us back to polymer science here. Mm-hmm. So I'd say an interesting point for polymers, especially when we talk about flexibility, is that a polymer is inherently viscoelastic. So if we give the greatest example of viscoelasticity, it's going to be silly putty. It'll just melt in your hand. It'll start flowing. But if you chuck it against a wall, it'll bounce right back. So a polymer has aspects of a liquid and aspects of a solid. Now, everything that we put in the body is not silly putty, but it has some of these viscoelastic material properties. So that means if you've tested kind of a flexibility under a basic tensile test, this is normally done very, very, very slow. And you then have a certain modulus. Now, when they're in the heat of a moment in a procedure and maybe incorrect and you need to move it a little quicker, you can have a very different response in terms of that material. So understanding kind of, you could have 2 materials that look exactly the same on a data sheet, but because everything is time dependent and frequency dependent, you could get very different like physician feels based off the same material, because they might be responding at a higher frequency than you would have tested. So it's important to kind of understand. And that's what I was saying. Yeah, there's no one point of a polymer. Yeah, it's all temperature dependent. It's all frequency dependent. It's a complicated world for sure, because these things do move over time.
You made a good point about it's not just about the polymer. It's about, the geometric properties, the wall thickness, the IDOD, And also, if I can throw in, processing, right? Some of the
Yes.
effects of processing, whether it's molding, reflow, extrusion, the proper processing parameters, or sometimes, you could make a mistake and realize, wow, this mistake actually created a pretty cool property that, for instance, like when you're extruding FEP, if you extrude it too fast or if there's too much shear, you're going to have this kind of orange peel effect on the outer surface, which might sound like a defect. But in some cases, that kind of orange peel effect, like on PTFE, or help the actual catheter glide through a guide wire because of the peaks and valleys. So that's sometimes a processing mistake can kind of actually be a benefit for the application.
Yeah, it's very important to remember a polymer does not forget.
Yeah.
It has a history, and no matter how it's been treated in the past, it will act accordingly.
Yeah, good point. Awesome. Let's move on to the next one. Really important, joining technologies, and that's kind of related to bonding and the compatibility of materials, right? We need to, if we're having a composite catheter with multiple sections and materials that'll be fused together, have to have chemical compatibility, temperature compatibility, or we run into problems. So let's talk about that one. And that's an interesting one for bonding, right? If we're going to overmold a hub to a proximal end, or we're going to solvent bond, or we're going to use some kind of laser technology, critical. Let's talk about that, Ned.
Yeah, I think it's just important to just realize you're trying to probably just minimize risk. This is another one of those things where we're expecting two very different properties to work together in the same device. We're using a lot of PTFE as a liner. PTFE is brilliant at not sticking to anything. That is why it's low coefficient of friction. But this also goes to the other side where it doesn't want to bond to anything either. And so we've inherently using a material that we know works very well for something, and then we're expecting to bond to something that doesn't want to do it at all. So we've done a lot of effort and experimentation and understanding that this trade-off is okay, but just be aware the fact that there's going to be joint or interfaces is a heightened point of where things can fail. And it's, if you see an issue, probably go to the interfaces first, because this itself within the polymer world is considered kind of a defect, and where things can happen more quickly than you might expect. Now we also, in the world of catheters, reflow, huge part of this, which means we have now liquefied everything in the middle and then cooled it back down. Immediately from that, normally you have a metal tube in the middle, and you have P-backs or other type of block copolymers. This is in terms of thermal expansion. And so inherently right around that, you're going to start seeing a potential issue. Now, we've done a great job of mitigating that within the industry, but just be aware interfaces plus residual stresses based off these kind of mismatch of thermal expansion is definitely a point to work or to be aware of, because it is where issues can potentially start.
Yeah, I think one of the top issues for recalls in a device catheter system is delamination, right?
Yeah.
Or bonding issues. And you're right about, like, for instance, PTFE, beautiful characteristics, but it doesn't want to bond. So you have to do other things like etching, so chemically etching or other means, or other materials that aren't compatible. You need tie layers and things like that.
Yeah.
It adds cost, complexity, and if you could ideally work with materials that are chemically and temperature compatible, you have a better product overall.
Yeah. And this is why you see kind of why P-backs is such a beautiful material within the space. A P-backs is going to be a block copolymer. So it's going to be a combination of kind of two different polymer materials, but they also then, there's tons of PhDs in the polymer world of if you change one chain versus the other in terms of length, they start doing a lot of different stuff morphologically. So you can really get a fine tuning of the properties of PBACs. And that's where I actually feel like we've seen some of the best durometer shifts within them without having to deal with these abrupt interfaces where delamination is most at risk.
Right. You're right about PBACs. People take it for granted, but it's probably it is probably for interventional catheters, the most used material because of the flexibility, and you can get kind of stiff up to 74D, and then kind of ultra compliant down to 24D.
Yeah, it's beautiful.
Yeah, and it's compatible. It can bond well, reflow like you talked about with a nylon 12, for instance, even some TPUs, right? Yeah. Excellent. Let's talk about, and we were kind of talked about bonding and being compatible, and one of those characteristics is temperature, right? And let's talk about temperature behavior, creep, and dimensional stability. And creep is an interesting one. I don't think a lot of people understand creep. If you can talk about some of those, characteristics for these materials, and again, I'm thinking, and you're saying you're kind of laying off the catheter side. I'm thinking on the catheter side of materials, depending on the application as well, need to be compatible from a temperature standpoint. But I'll let you kind of talk a little bit about that. It's pretty interesting.
Yeah, so I'd say creep goes back to what we're talking through with Silly Putty. It's the liquid kind of nature of polymers, in which if you put them under strain or anything, it will slowly drift over time. And this, because again, unless it's a cross-link system, so more of a silicone or other type of things, there will be chains that will be always moving. Now there's like some very important, so this thing called like the glass transition temperature within polymer science, in which it's a weird thing, for sure, but mostly if you want really steady processes, you want to be below this as much as possible. This would be more brittle type situation, but it also means your properties aren't really going to move. But we know there are some very important kind of temperature boundaries within kind of the medical device world. So most things are going to be shifting up to at least 37 degrees C to interact with the body. And then what I did not realize until kind of this research is how ETO actually is tested. In my mind, it's just a gas. It's okay. There's no real issues there, but that would technically work. But to expedite the process to make sure it doesn't take a week to sterilize your equipment, they run it at kind of like a little higher temperature and also humidity. So it can go as high as 60 degrees C, and it can go as high as like 80% relative humidity. So from that, we now have a very different environment interacting with the polymer, so it's mostly just be aware of where your transitions are within your polymer, because you can have properties that maybe start up here, but they start dropping a lot more depending on what temperature region you're working in.
I'll throw a curveball at you.
All right.
Just something I was thinking about that somebody told me, real smart catheter engineer, worked with materials, and we were talking about PTFE and alternatives to PTFE, and somebody threw out some alternative fluoropolymers, PFA and such. And he told me something interesting I never thought about, kind of related to creep, and maybe you can tell me if it is related to creep. But he said the reason that PTFE is such the gold standard for like balloon delivery for catheters is because it will cold flow at room temperature, meaning under load it'll deform at room temperature, He said, that's really what makes it soft. If you're delivering a balloon through there, it won't scratch the balloon. But if you're using a material that's kind of designed to be creep resistant, you're going to scratch a balloon. Does that kind of make sense to this conversation?
Somewhat. I'd say fluoropolymers are like the aliens of polymers for sure. So they're not going to play by the rules. A CF bond is going to make things really weird.
Okay.
We live in a carbon-based world, and then you throw in the CF, and stuff works really differently. So I don't have extensive knowledge of fluoropolymers because, yeah, it's pretty much rip up your usual rule book and buy a new book.
Okay. All right. Fair enough, Ned. I thought I'd throw you a curveball, but fair enough. All right. Let's move on to chemical exposure. We have, in some cases, fluids, solutions delivered through lumens, drugs, chemo, harsh drugs. We also have a surgical environment where there's cleaning solutions that can be cause damage to the polymers. So I wanted to kind of talk about that as what's the common failure modes related to chemical exposure.
Yeah, I thought about this a decent amount, and obviously the medical device world does a great job of minimizing any of this type of exposure. That we don't want it to happen unless you are specifically designed for wipe downs or certain type of things in which you will absolutely take into account that you're trying to minimize any type of crazing or any type of exposure there. I'd say kind of an interesting kind of two thoughts regarding this is thinking through kind of like with a large amount of hydrophilic coatings that we add to catheters, this itself could kind of be an environmental stress agent to the system as well. So you're working with normally some type of aqueous solution. So you're adding more, so waters plus nylons could always be an interesting play. And then if you add what we've talked about previously, kind of with ETO sterilization, this itself will, depending on kind of your environment or what you're truly testing. So nylons are super susceptible to swelling will absorb water very, very rapidly. So it's more to be aware. And then if we add another callback, it's going to be interfaces as well, where things are going to start pulling or start really interacting. So ETO exposure kind of within kind of the metal polymer interface could start, you could start seeing potential issues kind of with this. But again, thankfully, I'd say the medical device industry does a great job of trying to minimize this exposure, but just be aware that these systems change over time with the type of things we might think of it as additive in terms of like a coating, but at the same point, there is a chemistry associated with that can potentially kind of interact with our base material.
That's interesting. Never thought about that one. Hydrophilic coatings, yeah. You referred to sterilization a few times just a minute ago as well, and ETO, and that's huge, right? For a consideration for selecting a polymer, what modality will be used for sterilization, especially for thin wall catheters, right? There's just not a lot of meat there. Let's talk about the sterilization effects on material performance.
Yeah, so I think it's always important to understand from the material science perspective, what is going on when they're doing different sterilization techniques. So we're trying to kill anything, and there's a lot of different ways we can break a cell membrane. So ETO will slightly interact with the cell and cause it to disrupt. If we're using kind of radiation, that's going to just destroy everything. But then, okay, what does that mean on the material level? So I think an interesting thing to think through is also it's kind of it's a cross-linking versus chain scission issue. So it's not always apparent that there's some sterilization techniques that will actually kind of increase the modulus or the performance of the material. So if you use kind of radiation sterilization on a silicone, this will continue to cross-link the material even more. So causing whatever you measured like a stiffness before, it'll actually be more stiff. Now there's other materials like PTFE, which you mentioned before, which is highly susceptible to chain scission. So this means, as we talked before, you have this very long spaghetti of a polymer, and the radiation starts kind of chopping it up. And so now you have a polymer that's a much lower molecular weight, and your material property is going to be a lot different from what you kind of expected. So sterilization is probably the most aggressive of interface that your material is going to face. And you really need to understand that it will change your device and the performance quite a bit. So it's not just about did it fail or pass kind of different sterilization methods. It's okay, is our device still the same as we expected after the sterilization technique? So I think it's important to really understand what you're looking to get out, and what you're trying to minimize in terms of material properties changes.
Wow, excellent. So the guide walks through some of those characteristics and challenges, trade-offs.
Yeah, so part of the guide was I came from the polymer side, and it took me a very long time to kind of get up to speed within the medical device world, because there's not a lot of you have to piece everything together from a lot of different places.
Yeah.
And I know, biology was tough, and I still don't know biology well. And there's a lot of people that have been trained on the biology side and that have way more knowledge than I do, but there's no reason for them to expect to know everything about everything. So I was kind of frustrated with, I haven't seen this anywhere. So it's like, all right, I'll build it myself. And so
I love it.
This is kind of looking to try to find as many obscure properties as possible. So like, can I find elongation after exposure to radiation? Is that available so people can get an eye, versus just like somebody saying, well, this material will pass that. We know that because of this. Whereas it's like, actually it's roughly, again, ranges everywhere, but it's like maybe a 10% reduction in property versus something else. So that was the goal, is to try to just find as many unique properties at the same point, and then find 40 of them. Make it more easy to read.
Excellent. Well, this has been great, Ned. We covered 5 topics today, and we're going to get you back on to go over another group. This has been really interesting. For people that are interested in checking out the ebook or the guide, is it available online? Can people download it?
Yeah, so it's directly on the Saint-Gobain medical website, and we can definitely share a link with that for sure.
Okay, I'll put a link up.
Sounds good.
All right, Ned, this has been great. We're going to get you back. Thanks a lot for section 1.
All right, looking forward to section 2.
All right, thanks.